Well, first of all, I'd like to thank you for the invitation to come and speak to you. So it's a big thing to come all the way from Australia just to do 1.5 hour presentation, but it's been a bit of fun so far. I've nearly caught up on the what day it is, what time of the day it is, etc. So thank you very much. I'm going to talk, just follow on from what John's done. He did a really good background type of thing on what we're doing. So this one sort of might recap a little bit on it, and then I'll talk about some real measurements that we do. Just a little bit on the name of Sixarms. People have asked me how we came across the name of Sixarms, and it used to be called Innovative Drone Solutions a couple of years ago. We started out by saying we wanted a name change, and we started out saying it's the ARMS, we'll call ourselves ARMS, Airborne RF Measurement System. And then I said, no, we can't have that. I can't be the director of an arms company because it won't be so good when you're working around the country. So suddenly we put 6 in front of it, and then the 6 was because we use hexacopters. Anyway, so quickly I'm going to talk about what we are measuring, a quick recap on what drone measurements are all about, etc. Then I've got some case studies, and some of those case studies are real-world sort of problems that we've discovered through drone measurements. Things like the wrong feeder lengths, the main feeder's been cut to the wrong length, mechanical lean due to some storm damage, incorrect panel orientation, inverted panel, a panel installed upside down, what the effect of adjacent towers or structures will have on your main radiation pattern. And something that John talked about was how far do you need to measure. Measuring in the far field is what we normally do, and we've done some measurements in the near field to compare what they are in the far field. So what are we measuring? We're talking about, and I've focused this, although we measure shortwave and MF and military sort of frequencies and mobile phone type frequencies, etc. Try to focus this presentation on the broadcast aspect, and try and stick into the TV and the UHF generally, because I think that's what you're most interested in at the moment. So what we're talking about here is structures like this with an array mounted on the top. So a typical broadcast antenna is what we would say is a high power, can be multiple megawatts of radiated power, very high radiation or EME levels, so personnel and equipment can't get close to the array while it's broadcasting. They're very high gain antennas, and the antennas usually split into halves or quarters with an upper half, a lower half, and usually 2 or 4 main feeders, and that's for redundancy reasons generally. Very narrow beam widths, usually only a couple of degrees of a 3 dB beam width on the horizon. And typically there might be 4 faces of 12 panels, and each panel would have 4 horizontal dipoles for a horizontal TV service. So that's 48 elements on 4 faces, 192 dipoles. Typically they'd be 50-foot long antennas, maybe 600 feet above the ground. You know, what could go wrong really is the question we could be asking ourselves. And then so what and why are we measuring? What do we want to measure it for? So we're trying to measure what the antenna's radiated power is actually conforming to. If it's the correct amount of power, and where the power is actually going. So think of an antenna, it transmits antenna in all directions, a 3D sort of a thing. We do a horizontal slice and a vertical slice, and that gives us enough information to tell us the health of the antenna system. Call the horizontal slice a horizontal radiation pattern, HRP, and the vertical slice, a vertical radiation pattern, or VRP. So I'll use those phrases throughout this. So this would be a typical structure, and this is actually the EME levels on a structure, and it can go out, in this case it's out to 300 metres where we've got the crossover to a non-occupational limit for the EME. And at the top of the structure we've got a UHF array about there, and then a VHF array, and I think that's another FM array. So multiple arrays. The red is highlighting the occupational EME limit, and the yellow is the non-occupational EME limit. Why is it different on one side to the other? A directional array answers that one. So that's, if we do a slice vertically, then we'll pick up what the different peaks and troughs are as we go vertically from the ground to the top, and that might be looking what we call a VRP of one of the services. So a VRP, that is the horizon, that's 0 degrees, so that's straight out at the horizon. And down there is minus 10 or 10 degrees down, so that's towards the ground. These are real measurements done on a service, and there's 2 traces there for 2 different frequencies in the VHF band in this case. So that's one slice, so the VRP is done at 214 degrees true north, and coming down here is the amount of power coming down. And there you can see most of the power's about 0.7 of a degree below the horizon, which is about where you want to have it, and a bit of null fill there so that people live close into the transmitter they still get suitable sort of signal levels. And this is an example of what we call an HRP. Again, that's flying around at 0.7 degree depression, so that was the peak of the VRP, so we fly the drone around and measure at 0.7 of a degree down, and this is again real measurements in dBW, which is the scale from there down to there, and 2 different frequencies again in the VHF band. So that's purely as an example of what a HRP and a VRP is. Measurement techniques, so there's a picture of what we'd call our drone, one of our drones, Sixarms of course, and this is a log periodic antenna mounted above it, and you can see there's a couple of compasses sitting on there and a link back down to the ground sitting on one of the other legs as well. 3 of the propellers are orientated up, 3 of the antenna propellers are orientated down. That's so we can get 3 mounts sitting onto those arms above the propellers. So the hardware, what does it consist of? Is a vehicle with an antenna. We've got an integrated spectrum analyzer and PC sitting underneath there. You can hardly pick it up. Got a high resolution GPS and a telemetry link down to the ground control station. In terms of the software, we pre-program the drone with the flight path, and the drone actually flies an autopilot once it's up in the air, and it flies the path. If we're doing an HRP, it's a circle with the antenna obviously orientated towards the antenna under test, with the drone's antenna pointed towards the tower. And the software captures the information and displays the data on the ground-based station. So the actual software, what does it do? Of course it logs the software, but it discards invalid data, and that's data if there's a gust of wind and it blows the drone slightly off course in either of the 3 dimensions, then what we do is flag that data as potentially invalid. And so we enter into the software what the receive antenna of the drone's beam width, etc. is, so that the drone actually knows when it's off course, etc., to tag that data. Calculates the distance between the drone and the antenna under test, so it always knows what that distance is. So you don't actually have to fly a circle. You could fly an ellipse, a square, you can fly whatever shape you needed to do. It always knows what that distance is and calculates the path loss. We generally do a circle because it makes it easier for our brains. It calculates path loss, puts the correction factor in for the antenna, and it calibrates the feeder loss out between the antenna and the spectrum analyzer. Generally we have an attenuator sitting in there because the amount of signal that we get in that close is too much for overload, so that 10 or 20 dB attenuator is part of that calibration factor. We actually determine the absolute power And it puts the results on a template, and the template would be the manufacturer's what he thinks it is, and we plot the real figures on top of those. And so the guy on the ground can actually see live it actually plotting on top of that template. So it's so the methodology, what do we do? Basically, there's about 7 steps in this. One is we want to determine where the actual antenna is. So we use a highly accurate GPS, and it sits there for 20 minutes, half an hour, to get a very good fix on the actual position of the base of the tower, generally is where we would put it. We need the height of the antenna that's under test. Generally we'd use tower drawings, or if that's not available, then we'd use a theodolite to pick up the centre height of the antenna that we're going to test. We determine what the far field distance is, and that's really a factor of the frequency of operation for that antenna and how much aperture it takes up on the tower. So, but as a rule of thumb, think of an FM antenna as 450 feet or 150 metres. Well done. The VHF antenna might be about 1,200 feet, and a standard sort of UHF, large UHF array might be 1,800 feet from the antenna. So then we program in the VRP runs into the drone to the autopilot. If there's 4 faces of panels, there'd be 1 VRP per, 1 run per face of those panels, down the bore side of each of those panels. And we try to get 10 degrees above the horizon and down as low as we can before we run into trees, houses, or whatever it might be. So the widest range of VRP run. This is one of the advantages of using a drone over a helicopter. A helicopter usually can't get that low above houses or trees as a drone can, and the drone can actually be closer, so you get a wider arc of VRP, which is one of the key advantages. Then we fly the VRP, the vertical radiation pattern runs. You know, these are the 4 out to the sides, 1 on each of the bore sites. And there we review what that information has given us, and that tells us what the peak of the VRP, the tilt, if you like, of the vertical pattern, which is generally about 1 degree below the horizon. Then we program in the HRP run into the drone, and the drone will then fly around that 1 degree circle around it. You see that might be a picture looking down the bore sight to the tower, if you can see that. This over here is a typical run. Each colour represents 1 run, and you can see the yellow, we made it only 3/4 of the way around, and then our battery started to run down. So we fly back to base, change out a next set of batteries, continue on and do the blue run with the replacement batteries. Doesn't matter, the drone in the software picks it all up, knows where it is, and makes one contiguous file at the finish of that. A typical accuracy that we're talking about is absolute, about plus or minus 2 degrees in this particular case. It does change if you're doing FM or VHF TV. It does. There is a few changes, but typically it's 1.8 to about 2.6, I think, is the range of stuff that we've done. And of course, relative's a lot better in those cases. So that's the sort of accuracy we are talking about. So moving on to some case studies. This is the case where we've got some main feeders cut to the wrong length. Most antenna systems, you have 2 or 4 feeders coming from your transmitter up to your antenna. And the antennas are, you know, they're separated physically on the tower into halves or quarters, and each feeder feeds one of those halves or quarters. So obviously then the length of those feeders is quite a critical length, and they might be hundreds of metres of long, and they're cut to be within millimetres of the right length. So that length being critical. If they're wrong, you're going to get a beam tilt up or down or some other effects similar to that if you've got quarters. So if you do your HRP, you may not pick it up, but if you do your vertical runs, you will pick up what the effect is. And it starts to look like this. So the black line here is what it should be doing. That's the manufacturer's data, the original design document. The measured data that we measured with the drone is this one here, the coloured, and that's for 2 different frequencies. Again, it's a VRP on one particular angle, and that's the horizon there. That's 1 degree down, that's 2 degrees down. So you can see that the peak of the power is 2 degrees down. But if you lived out on the horizon where you really want the power, you can see the difference from what's actually happening to what you should be getting. So, and that's people on the horizon will miss out, or were missing out on the power, and that was where the original complaint from the broadcaster came from. Case study 2 we'll talk about is mechanical lean from storm damage. So we've got large UHF arrays. They've got a very narrow beam width, as I was saying. All the power's basically pushed out to the horizon. Typically 2 degrees is what we're talking about is in terms of a beam width. So a small, if you get a storm in there, mounted there, you can get a lean or a bananaing can sometimes occur. So if you've got tilt on one side, it's going to put that beam above the horizon on one side of the tower and down into towards the ground on the other horizons. So in one case we sent the ringing team up there and they went up with their spirit level. Didn't start, it's vertical, not a problem. So we went out and measured with the drone. In this case the theodolites couldn't pick it up because it was housed inside a big radome for weather protection, snow protection. And so the VRP measurements actually showed what the problem was. So on one side of the tower, we're talking about, this is on 85 degrees and that's on the other side, the other face at 229. You'd see what it's supposed to be, the black trace in both these cases is what it's supposed to be. We're about 1 degree down on one side and half a degree up on the other side. And that's a bananaing type of effect that occurred. By the way, it's not this tower that was causing the problem, it's another one, but that was a nice picture. So VRPs picked up that, and then the riggers, interestingly, then went back up to the top of the array, this time with a string and a weight, put it at the top of the array. They measured about 1 foot out at the bottom, and when we did the calculations, yeah, it was about 1 degree. So, you know, in this case, sometimes the drone was actually better than the riggers' initial value assessment. Case study 3, this is where we got a panel orientated incorrectly. So again, dozens of panels sitting there. Occasionally during installation we might have an error, it does happen. And panels can be installed on the incorrect bearing, and the HRP will actually pick this up. So in this case, this one was not UHF but band 3 TV. That's the sort of antenna that should have been orientated as per the black line there. The drone measurements is the red data, red line sitting around here. So people sitting out here at 330 degrees should have been getting this sort of level of signal. What are they getting? 1/4 of that sort of signal going in that direction. So again, a coverage complaint triggered it with the broadcaster. They engaged us to come and measure it with the drone. We found that, and what happened was they needed to reorientate that panel back to where it should have been. For whatever reason, when it was originally installed, it was offset. The inverted panel, similar sort of case. We've got large arrays, lots of panels, and occasionally errors can occur, and the panel can be inverted or upside down, etc. The HRP and the VRP will show that, and the case in this case looks like this. Whereas this should have been a contiguous circle around there. One of the panels, it was 3 faces of panels, one of the panels was inverted upside down, which created this huge hole in the coverage pattern there. The reason this, by the way, this is not measured because that was the side of the hill. It was a tower on the side of a hill, so no point in measuring into that side there. Now, adjacent tower or structures, this is quite an interesting one. So quite often you've got a structure and nearby you've got other structures. What are those other structures going to do to the radiation patterns? We've got a couple of cases that we've measured here. Now in this case it was a 5-sided array. Again, the black colour there is what it's supposed to do according to the manufacturer, etc. Green trace is what we actually measured. And look, there's an adjacent tower 650 feet away at 200 degrees, and that's down here in the circle. And what that does is put a 3 dB notch into that array, about 5 degrees wide across there. So that's one single structure in this particular case doing that. In this case, these are multiple frequencies, that's why it's multiple frequencies sitting here. The adjacent structure, we have one at 160 degrees at 170 feet away, so closer, and one at 190 degrees, but further away at 540 feet. And you can see this is a 7 degree notch sitting in there due to this structure there, and a lesser, a 4 dB notch sitting in there due to the one at 450 feet away. So they're quite a distance away, but they're still having quite an effect on what the pattern is. So I wonder when we get to something looking like this, we haven't measured this one yet, but I'm looking forward to the day that we do, that if you owned something right in the middle of there, and it was lower than the rest of the structures, you'd be asking for a tower extension probably if we actually measured it. Let alone you get to the candelabras like this, I'm not sure of the effects of the adjacent structures on the same tower. Looking forward to doing that one day. So case study 6, just about on time, measuring in the near field. Now I talked about we did measure in the near field, that's what we want to have in the far field. And the reason we do that is if you're in the near field, the electric field and the magnetic field are not stabilised. So if we want to measure power, and if we're only measuring the electric field, you need to be in the far field for that to reflect what the true or absolute power is going in that direction. So in the far field, if you only measure the electric field, you can derive the power, and that's relatively accurate. Once you get inside the near field, then measuring just the electric field won't give you what the actual power is accurately. So we decided to try and how, in the real world, what was the difference. So in this case, we did several different distances from the tower. And this structure, which I'll show next, it actually consists of 4 faces of 16 panels, a UHF TV, and the far field in this case, since it's a relatively high frequency and it's quite a large aperture array, the far field distance that we'd normally do is 4,600 feet. So we got plots below that I'll show you. We did it at 1,000 feet, 2,000 feet, 3,800, and one much further out there past the far field. So we were interested to see what the comparison was practically. And this is what it sort of looks like. So the three, again, let me explain this. This is the amplitude down here, the magnitude of power, and out here is, along here is, that's half a degree beam tilt, 1 degree down, 1.5 degree and 2 degrees down on the horizon. The orange trace, this one up here, is from 300 metres out, and 300 metres. So we did 300, 600, and these distances out. Now we can start seeing what the power is. So at 600 metres out, 2,000 feet out, instead of doing the far field being at 4,600, let's say half of the distance, I think we could say we've still got useful results, but if we come into a quarter of the distance at 300, we're starting to see things change shape. Interesting, the magnitude stayed about the same for the first 3 readings. Only when we got to 300 metres did the magnitude start to change. So if you are pressed because of land quality, land, mountain restrictions, flying in the near field isn't as stupid as it might seem. Still gives you some valid and useful results. I think that's just about my time within a minute. But thank you very much. If you've got any questions, feel free.
When you're flying close in like that I would assume one of the ideal things, you can still find problems like you mentioned earlier on, like with inverted panels and other types of mounting issues. They would still show up but not, it's clearer when you're further out and everything combines, but you can still find the, wait a minute, you got that null.
Yeah, so look, the concept of doing this is to say, is it as per the design?
Right.
And if the design hasn't been implemented, i.e. with a panel upside down, you'll have some effect that shows either in the HRP or the VRP.
I've heard of cases.
So no matter how far.
I've heard of cases where like a pylon antenna, slotted antenna, UHF, was rotated out, half 180 degrees out, and I'm sure we could still find that with a close-in look, with a close-in fly.
That's it. The other thing I'd say is, look, it's worthwhile, and it's another case study I said. We found an inverted panel, and what it was putting a hole, a lack of null fill, at a close angle 5 miles out. Everybody in that area received no TV.
That's
now,
very impressive.
Roll on 20 years, so they put in masthead amplifiers. Roll forward 20 years, and we discover that the antenna has been installed correctly 20 years ago. So we talked to the broadcaster was then left in the dilemma, do they actually fix it or not? If they actually fix it and put it back, then all of those masthead amplifiers close in are now going to be overloaded. So the broadcaster in this particular case decided, no, I'm going to leave that as it was faultily installed. So I guess the lesson out of that is do a drone test as soon as possible after it's been installed before there's an established viewing pattern from the error. Yeah.
Yeah, I'm curious what kind of, whether you had to write your own software to set the parameters for pitch and yaw and those kinds of, what kind of tolerance did you use for those factors so you have to discard your data or not? Yeah,
so it varies depending on what the receive antenna is. So, and that comes back to the accuracy table that I showed. So if you want to have a more accurate accuracy, you can actually pin those down so that instead of having the beam width of, for instance, plus or minus 3 dB, you bring the beam width right down to plus or minus a couple of degrees, and therefore the magnitude of error that we quote will be much tighter tolerance. It didn't quite come out right. What I'm saying is if you have a dipole versus a highly directive receive Yagi, then it makes a difference on what those clipping factors are, the pitch, roll and roll. Yeah.
Do you have the log periodic antenna set up so that you can orient it for vertical polarization as well?
Correct, yeah. We got a mount system which makes it a quick change so that you can leave the antenna basically on there, quick change from one to another. And so we don't only just do TV stuff, we do stuff for mobile phone carriers and the like.
And then on the close-in, the near-field measurements, generally you can find that you should be able to do the azimuth pattern without the concern of the, considering that it's a near-field versus far-field because of the fact that the elements themselves are small in diameter.
Yeah, so the near field, far field is not to do with the receive antenna, it's from the broadcast antenna.
Right, right. But the broadcast antenna has identical elements that are arrayed vertically, so the physical size of the antenna is small. The D is small for azimuthal patterns as opposed to the vertical pattern.
So you're absolutely right, except we want to measure the absolute power by only measuring the vertical signal, not the magnetic signal as well.
Right.
So if you want to get back to absolute power, you need to be in the far field.
Got it.
That's what we need.
Would you have to inject a signal into the main transmission path so that you could synchronize, or could you just use the main transmitter?
No, just use the difference in the path lengths. So is that what you're asking? It's the ground reflected signal?
Yeah, essentially, I mean, gating it out, but you need to know what you're transmitting, and you need to be able to time sync the two measurements, right?
Well, that's one way of doing it. Or the other way is that you're getting two signals. One is the incident signal, and the other one is a reflected signal, which is arriving later than the incident signal. So you set up the spectrum analyzer with a gating front end, which only accepts the incident signal and rejects anything arriving after a period of time.
I know, but how do you synchronize that? From like, how do you know which is the first and which is
Well,
the second?
it's a work in progress, so you tell me.
I mean, like with a network analyzer, it's a synchronized signal, right? So
Yeah, that's right.
You can gate directly. So I wondered if you injected a known signal into the transmission path, you would then essentially you would have control of the system. Then.
No, I understand your concept.
Yeah, or you would have a method of measuring what was being transmitted anyway.
Yeah.
I was just interested.
To be honest, at the moment, the ground reflected signal hasn't been an impediment to us. There will be some sites where it will be, and I think John talked about something over seawater. We've done it over seawater. We get at close to the seawater level, you get some. As soon as you get up where the midpoint reflection is back on land, then it's fine.
Yeah, and you were generally measuring high gain antennas, so it's maybe less of a problem. Yeah. It's the lower gain you're going to have the problem with the wider beam.
That's it. So when you get close to the ground, where you get poor rejection or discrimination from your receiving antenna.
Yeah. Okay, thank you.
Ian, thank you very much.
That's all right.
On behalf of IEEE BCA.